So confidence interval, in fact, is a range of values which are calculated from sample data and is likely to contain the true population parameter. The examples could be the population mean, proportion, but most importantly, we use confidence interval to find the true population difference between two means or proportions of normally two cohorts. For example, you might remember that in chapter 2, we calculated the difference in diastolic blood pressure between males and females, and then we also looked at the confidence interval for that particular difference. Let me run it again. I am going to task and utilities under task, under statistics. I clicked on t-test. Under data tab, fhs underscore lib.heart, data is selected, and I'm going to choose two samples, t-test, and diastolic blood pressure is my analysis variable, and sex is my grouping variable, and I will submit the code. Okay, so here are our results. Okay, so if you see I think this is the fourth table from the top. The actual difference between males and females is in the sample is almost 1.6 millimeters of mercury, right? But this is the difference for the sample itself: 2,336 males and 2,873 females. But right next to the actual difference in the sample, the statistical tool SAS is also calculating the 95% confidence interval, which is in fact telling us that the true population difference ranges from approximately 0.88 millimeters of mercury and approximately 2.29 millimeters of mercury, showing that in the females, we see that in this sample of 5,209 individuals, the diastolic blood pressure of female is approximately 1.6 millimeters of mercury lower than males, but the true population difference might lie somewhere between this value and this value, meaning that if we repeat the same test with same number of individuals from the same population again and again and again, say 1,000 times, in 950 times or so, we will get the difference somewhere between these values and this value. Because the thing is that the next sample of 5,209 individuals will be slightly different, and of course there will be a natural variability from sample to sample to sample, right? So every time we'll find a very different, not very different, slightly different diastolic blood pressure, but we are 95% confident that the range in 95% of our samples, the values are going to be between these and these values. Of course, we will never be 100% sure, but at least with this 95% confidence, we can say that the true population measures might lie between this and this value. And because even at the lower end, it is not including zero, it is still showing some difference. We conclude that there is a statistically significant difference between the diastolic blood pressure of males and females. So as I said, in health research, we use normally 95% confidence interval, which implies that if we repeat the test multiple times with a random sample of the same size, approximately 95% of those values would contain the true population parameter. During our demonstration of the CLT, central limit theorem and empirical rule, we observed that 95% of our sample means fell within 2 standard deviation and approximately 68% fell within 1 standard deviation. But the thing is that in real world health research, taking multiple samples, 1,000, 500, or even 100 or 200 is impractical. We must have a reliable method to estimate confidence interval from a single sample, right? So the good news is that statistical theory provides us with a method to calculate these confidence interval pretty accurately using just one well-collected representative representative sample.